In this presentation, we are taking a look at how we can create a derivational search function for a recognition grammar or for a class of recognition grammars. Before I go to the implementation, I just want to point out that this approach that I'm presenting here, it's not a derivational grammar for every type of recognition grammar. Rather, I have selected a narrower class of recognition grammars. What this class is, I don't need to define here because we will see it in a very concrete way when I go into the implementation. But it is just one possible approach among many. And derivational search function, to summarize or recapitulate, was a function which explores all the empirical consequences of our hypothesis or model. And the recognition grammar is a generative grammar in which the set of expressions or meanings or pragmatical context, whatever it might be that is in our dataset, is defined by defining or providing the characteristic function for that set. So instead of enumerating a list of expressions from some input elements, this system will read individual isolated input expressions and recognize whether they are, let's say, grammatical or ungrammatical, meaningful, non-meaningful, attested, non-attested, whatever it might be. But let's go directly into the key issue. Here is first an illustration of the type of recognition grammar we will be discussing here. So we will have input expressions like the dog barks, and the input expression will consist of a linear sequence of words, here the dog and barks. And we will be consuming or processing each input expression from left to right. So this is what the arrow here signifies. The arrow represents or illustrates. We go we do something, then we process dog, we do something, we process the verb barks, and we do something. And when I say we do something, I'm talking about what linguists would call cyclic computations, which means that we are applying the assembly operations immediately after these words have been detected and consumed from the input. And then we will have the phrase structures we are constructing by these cyclic assembly operations here. And what is happening here that every time we consume an input element from the input expression, one word at a time. And what I'm not showing here is that we will, of course, retrieve the corresponding primitive constituents, lexical items from the lexicon. That's part of these operations here, but it's not illustrated. We do that, and we then merge these primitive constituents to the right edge of the phrase structure that we have in the working memory at the time each item is processed or computed. So first we have the definite article. This is in our working memory. We consume the next word dog, and it's merged to the right side, to the right of that primitive constituent representing the definite article, shown here. And then when we receive the verb, we will merge the primitive constituent to the right of the noun phrase that we had in the working memory. And the operation is called merge right because it will always be merging or attaching the incoming primitive constituent to the right side. And this is because we are only generating phrase structures which are consistent with this linear order here, meaning that every new word always have to be linearized to the right of everything that had came before, and to have it to satisfy this condition, it has to be always merged to the right edge, because the linearization algorithm will use the left to right and left first algorithm or method. And that's the basic idea. But one of the things that we didn't pay any focus here, that you might have already noticed, is that here when we are merging this last item, we are merging it to the right edge, to the right of the noun phrase, as I'm showing here. But there is another possibility. We could merge it to the right of the noun. And the two possibilities are illustrated here. Both of these options are consistent with the input expression and its linear order. And although in this case the second representation looks linguistically implausible, there are cases where we really would prefer that option. For example, if the input expression would be the angry dog, in that case the dog, the noun, would be most likely merged into the position shown in example 2. So it would be the angry dog and not the angry dog. You see the difference. And so on, you can start imagining different kind of examples and notice that often both of these, or there could be many more possibilities where the incoming constituent could be merged at the right edge, depending on how complex the phrase structure in the working memory is at that moment. So you can see that we can't often rule out some of these choices. It depends on the type of words there are in the input expression, and also it will depend in many cases on what type of words are coming further down the line, words that we have not yet processed or registered, because remember, we go word by word. What we have to do therefore is, and let me point one more thing, we can also have situations where the input expression is ambiguous, meaning that there are actually several choices that are both correct. Anyway, what we can do here is that we will now build the recursive backtracking on the back of these choices, so that at each time when the word, we are processing the incoming word, like the verb here, barks, we will create now a list of all of these positions at the right edge that are possible. Perhaps we can also order them on the basis of how plausible they are, but I put that aside here. And then we use that list as a basis of recursion and backtracking. I will show the code soon, but to illustrate it here, when we consume the word barks, we will notice that we have these two options, and we put them into an order or list, and then we go take the first item from the list and we recursively move to the next word. If there would be, for example, the dog barks in the garden. So at this point, when we are processing the barks, we make these both options into the list and we go recursively into the first one and consume the fourth word. And then we continue until do the same for each word until we reach the end. And we have a complete phrase structure with all the words processed and then we use these lists for backtracking each step. That's the function now we're going to implement. Okay, so let's go to the implementation then. This is first of all the script is again in a templates project. And then the script itself is this template 4. And this is a starting point or entry point script for a simple recognition grammar that is based on the model I just described informally. Just to make a few quick observations if you want to work with this script. So here we have already a separate lexicon class which handles all the lexical processing. It's a bit more advanced script than what we have looked so far. And then there is a phrase structure which is implemented just for the sake of illustration a bit differently. But what is important here is that I'm using now a list and not the asymmetric pair. And list because the right edge merge operation requires that we modify existing phrase structures. And that's more easier with the list because this ordered pairs or tuple representations doesn't allow any kind of modification. We would have to redo everything. So here is then the derivational search function for this type of system that we just defined. It takes its input. First there is the phrase structure in the syntactic working memory that we are constructing. And then there is a sentence, the input sentence, which is a linear list of phonological words. And then an index, which is pointing to the word that we are processing at any time. It begins from 0 and it runs through all the words in the list. And as you can see here, in the recursive call, we always move to the next word by adding 1 to the index. The first thing we do here is we check if there are still more words to be processed. And if the index is the same as the length of the sentence itself, this means that the index is pointing actually outside of the list. And then we will process the final output. For example, we can check if it's well formed, if it satisfies additional semantic or syntactic constraints. And it will also create a semantic interpretation. But if there is words to process, we go here, and then the first thing we do is we look at the word from the list based on the index we are currently. We retrieve the corresponding lexical item, or in fact this returns a primitive constituent. And this is implemented by its own lexical class or module. And here we have then the new primitive constituent. And now there is something non-trivial here, but the basic idea first, what this recursive loop is doing, it is considering all right edge positions of the phrase structure X in the working memory. And then it will create a new X, new phrase structure by implementing the merge right operation into that position. So this is the step where the parks, for example, is merged with the noun phrase. And then we call the same function recursively. So we have the new phrase structure resulting from that operation, and we call this function again, but we move the index further, so we consume the next word in the list. So this is the, and here we, as I mentioned already, we put all possible right edge positions, explore them all systematically. And then when we go for the recursion here, later we explored all of that, we backtrack to the same place, and then we can consider the next position at the right edge and do the same. So that creates the recursive space for this type of recognition grammar. But there is one non-trivial thing that we have to pay attention, and it is that when we create this merge right operation, we are changing the phrase structure. But when we are in this loop and we backtrack at some point back to the same place, we have to be able to work with the phrase structure that we got as an input to this function, and not with the modified version. And so for this reason, we have to create a copy for the phrase structure in the working memory, its own copy where we implement all these operations, and that's what happens here. So in this way, when we return and backtrack to the same loop, we will have the X, the original phrase structure, still intact when we try another solution. But the problem is that if we make a copy, then the right edge position that we designated in the loop is pointing to a right edge still in the original phrase structure. And so for this reason, what I'm doing here is that I'm actually, the loop is, it's counting the nodes in the right edge position from 0 to how many there are. It creates an index I for those positions here. And then when we do the right edge, when we consider the right edge into the copied phrase structure, we take the same right edge position based on that index and not the node itself. So that's what I'm doing in this code here. I think that this could be done in a more elegant way, and perhaps this is not a good way to do this, but that's what I have done here. But the problem is real and has to be solved in some way. We have to, each recursive branching has to use its own copies if we tamper with the elements. So that's a slight complication. But otherwise, I think this is fairly clear what this is doing. Let me check this merge right. Here is the merge right function. And as you can see, it's slightly more complex than merge. And this is because we are inserting the incoming word inside of an existing phrase structure, possibly. We are not always merging it to the topmost position, but sometimes we go inside, and that requires some extra steps. That's why it's slightly more complex. Now you can try this script. It reads a dataset from the same directory automatically and produces output. I'm not going to look at the all output. I'm just showing one illustrative example. So the first examples in this dataset are simply linear sequences of A, B, C, and D. And this is the output from this script that I just showed. And what's happening here is that if we have just one word, will produce that. If we have two, we have only one way of putting them into a binary branching phrase structure, and that's what this algorithm finds. So this is the only phrase structure that is consistent with this linear order. Example 3, we have 3 elements, and it finds now 2 possible phrase structures consistent with that linear order. And this corresponds now to the dog barks example that I looked earlier. If we have 4 elements, it will find 5 different ways that could have been generated given those assumptions. And this order here in which they are explored now corresponds to the order in which the merge right function that provides, the right edge function which provides the list will provide these items. So here, because if you remember, it determines the position by index starting from 0 and going downwards. So the consequence is that the first solution that we find is always one where every incoming element is merged to the highest right edge position. So we have this representation here. And then you can see it starts the backtracking. So then it decides that maybe this D that was first created, put in the highest position, it considers, well, perhaps it was wrong, perhaps it should be merged as a sister of the C. And so we have a solution, the second solution, where we have 2 binary constituents, each having 2 daughters, and so on. And then 5 words, we get much more solution. And then in this script, I did some realistic modeling already. The dog barks is here, it finds only one solution because the lexicon contains some selection properties which are able to rule out the implausible derivation. Where is this happening? Well, this could be implemented in the post-syntactic function or inside the derivation itself, as I explained earlier. Here it is checked from the final result. And here, sentences 7 to 11, these are now ungrammatical expressions. So what happens here is that the recognition grammar will not find any acceptable solutions and judges them ungrammatical on such basis. Then we have a transitive sentences. You can see that these are not completely implausible solutions, although this is very simplified grammar model. Well, that was it. Simple derivational search function for a class of recognition grammars that in my view, could serve as a starting point for, I think, quite a plausible and interesting model.